Constant pressure calorimetry. All right, in constant pressure calorimetry, we are going to be talking not about delta E, the overall exchange of energy. We're going to be talking about a different state function, and that state function is enthalpy, delta H. The enthalpy of a system is the sum of its internal energy of the system and the product of pressure and volume. So when we're doing this reaction, typically constant pressure calorimetry would involve both thermal energy and work energy. But here in our setup, a lot of our reactions are undergone in a liquid solution, and therefore the change of volume in those is relatively small. And so even though there could be a little tiny bit of work done, volume can be changed. If you think about the higher the temperature, volume does expand a tiny bit for liquids, but we're going to assume that that is negligible. So what this type of state function does for us is it actually prevents us from needing to quantify work. Enthalpy change, delta H of a reaction, is going to be directly proportional to the heat evolved in the reaction at constant pressure. So again, just like delta E was equal to Q for our constant volume calculation, constant volume was a little easier because work was zero, because there was no change in volume because we were in a bomb calorimeter. Now we aren't in a bomb calorimeter. We're able to see some pressure volume work, but we're gonna just ignore it because it's super hard to calculate it for liquids. So delta H and delta E are usually similar in value. The only time they are different is if we have gases produced in the reaction. When delta H is negative, just like delta E, heat is being released by the system. This is what we call an exothermic reaction. Surroundings start to feel hot. So when we're holding the cup of an exothermic reaction, we're like, ooh, heat. The system is not getting hotter. You are the surroundings. You are feeling the heat coming off of the reaction, out of the reaction, exiting the reaction, being absorbed by you, the surroundings. So the reaction is not hot. The surroundings is absorbing heat from the system. And so that means that the surroundings is getting hot. And the exact opposite, if delta H is positive, just like delta E, heat is being absorbed by the system, and that is an endothermic reaction. So that's when we start to feel cold. We're like, oh, it's getting chilly. And the reason for that is because our heat is being pulled away from us and put into the system. Again, we are the surroundings. The particulate view for an exothermic reaction. Thinking about the particulate view, we're talking about the molecules themselves. The temperature of the surroundings rises due to a release of thermal energy. This extra thermal energy is coming from the conversion of some of the chemical potential energy, the bonds, in the reactants into kinetic energy in the form of heat. So that could be bond breakings or bond forming, looking at the idea of movement, right? So during the course of a reaction, existing bonds are broken and new bonds are made. So the products of the reaction for an exothermic reaction, the products have less chemical potential energy than the reactants. The difference in energy is released as heat. Opposite for an endothermic reaction. Existing bonds are still broken and new ones are made, but the products of an endothermic reaction have more chemical potential energy than the reactants. So to acquire this extra energy, some of the thermal energy from the surroundings has to be converted to chemical potential energy and stored in the products. The enthalpy change of a reaction itself is an extensive property. So the more reactants you use, the larger the enthalpy change. By convention, we can calculate the enthalpy change for the number based off of the number of moles written in a reaction. So looking at this combustion reaction over here, propane, C3H8. Propane is something that you most likely see in barbecues. It's a gas. We pressurize it and put it into a container. And then that's usually under the barbecue, right? And then you light it on fire, and the oxygen from the atmosphere reacts with it to form carbon dioxide and water. And it also releases 2,044 kilojoules of heat per mole of the reaction. So that could mean 2,000 kilojoules per 1 mole of C3H8, or 2,000 kilojoules per 5 moles of oxygen. So that per mole idea, this is technically going to be written in kilojoules per mole. They usually don't write the per mole there. I'll start writing it just so that we can remember that it's there. But per mole of what, Lauren? Be specific, right? You always tell us, be specific. Per mole of what? Per mole of whatever the coefficient is in front of the molecule you want it to be in front of. Measuring delta H, calorimetry at constant pressure. Reactions are going to be done in an aqueous solution, so typically in water. The calorimeter is often used in a styrofoam cup. Why do we use styrofoam? Well, styrofoam is a polymer. Polystyrene is its chemical name. It is an organic molecule containing a lot of carbons and a lot of hydrogens. And so the reason why we use it is because it is a great insulator. It does not like to release heat. That's why most coffee places give you styrofoam cups or some sort of derivative of styrofoam. And having a lid on the coffee cup calorimeter is always a good thing indeed. It keeps that heat inside. But if we wanted to look at the actual inside of this cup, we would have an aqueous solution. Water is the solvent. H2O as that solvent is going to be the surroundings. The reaction particles themselves are the system, right? So we have reaction particles here. We can call that the solute, and that is going to be the reaction itself, or the system. So be very, very careful with what we're actually measuring the temperature of. The thermometer will still be measuring the solution, which is the surroundings, all right? Because the majority of the solution is water, and that is of the surroundings. So when we measure things, we are going to be measuring the mass of the solution, the specific heat of the solution, which will typically use water, and the change in temperature of the solution. These are going to be the same magnitude but opposite sign of the reaction. We're going to practice with this a lot, but it's really important to note that when we start using thermometers, we're measuring the solution, which is going to be more geared towards the surroundings itself. Let's practice. Magnesium metal reacts with hydrochloric acid according to this following balanced equation. In the experiment, we're going to determine the enthalpy change for the reaction. We're going to find out what delta H is for the reaction. We combine 0.158 grams of magnesium with enough HCl to make 100 milliliters of solution in a coffee cup calorimeter. Now, when the HCl is sufficiently concentrated so that the magnesium completely reacts, the temperature of the solution will rise from 25.6 to 32.8 degrees Celsius. We're going to find the delta H. We'll assume that the density of solution is 1 gram per milliliter, and the CS of the solution is that of water. All right, let's get everything organized and set this up. The key here is that it already gave us the amount of the solution. Yes, it gave us the amount of magnesium as well. We're going to use that later for moles of the reaction, moles of magnesium in this reaction. But it says that 0.158 grams of magnesium is mixed with enough water to make a final volume of 100 milliliters. That is going to help us to find the mass of the solution. All right, we know that 1.00 grams over 1 milliliter, the density from up there, means that we have 100.0 grams of the solution. There's our mass. Specific heat capacity, 4.18 joules per gram degree Celsius, and delta T, final minus initial, and do the math. Don't forget, subtraction and addition sig figs are different than multiplication sig figs. 7.2 is our change in temperature. So Q of the solution is equal to the mass times the specific heat capacity times the delta T, and that is going to be equal to 100 grams times 4.18 joules per gram degree Celsius times 7.2 degrees Celsius. Q of the solution is going to be in 2 sig figs. I'm going to go ahead and convert this into scientific notation for us because of that 2 sig figs. 3.0 times 10 to the 3 joules. Awesome. I know that my Q of the reaction is then going to be equal to negative 3.0 times 10 to the 3 joules. Pop a negative on there. How do I know that makes sense? Heat is released from the reaction. The surroundings increases temperature. Exothermic reaction, surroundings gains heat. Reaction releases heat. For the last step, we want to find the delta H. The only difference, again, between Q of reaction and delta H is including the moles. We are given the moles of magnesium, and so we will use those. Negative 3.0 times 10 to the 3 joules will be our Q. We had 0.158 grams of magnesium. If we look up on the periodic table, the molar mass is 24.31 grams. So what does that mean for moles? Very, very small number, 0.00650 moles of magnesium. And we'll put that in the denominator. 2 sig figs at the end of the day, negative 4.6 times 10 to the 5 joules per mole magnesium. Beautiful. Zoom out. Negative 4.6 times 10 to the 5 joules per mole.